welcome to another episode and session about data drift, sensor drift. Let's maybe first look into what is it and who's better to ask these kind of questions than our friend ChatGPT. So what we can see is that sensor drift is the gradual deviation of a sensor's output from the true reference value over time, even when measured conditions are remaining constant. So that's apparently the definition. And maybe Thomas would be good to explain it a little bit more in detail using this example of a pressure sensor.
Yes, this is a very simple picture of the most basic type of drift you can imagine. The true value remains exactly constant. That's the black line, and you see that the value starts to deviate from that line, basically suggesting that the pressure is changing, whereas in reality it is not changing at all.
Okay, the reason why we talk about drifts is simple, and in presentations, keynotes, on stage, I tend to use this metaphor, taking a compass or even taking two compasses and making the jump or the thought exercise. What if north of your compass wouldn't really be north? And this is an analog instrument signal, and you would use that signal as an input for your AI model, your twin, your data product, your operator would look at it, your automation system would use it. That's the kind of step we're going to make, because you could say like, okay, drift, a couple of percentages off, that's not a lot, but the navigation, even 1-2% off, you can end up on the wrong continent in the end. So that is why drift is important, and that's what we're going to talk about today. For drift of sensors, what you see is why drift is happening. A lot of the things are related to aging of the component, like wear, degradation, calibration loss, but also like environmental losses. And something that not a lot of people talk about, but imagine again that compass, and you would say like, okay, we have tempered the compass and we used magnets. Also, that can cause off signals, wrong signals, and drift over time. So we're going to talk about drift in detail related to sensor data. Now, relating to the definition, this is something that has been covered before in videos that we've done. Data quality management, data defects, data downtime. What is data downtime? Well, data downtime was the periods in time where the data cannot be trusted because of the data is partial, missing, erroneous, or inaccurate. And indeed, drift is one of the features where you could say like the data is not reflecting the actual state of the underlying process. Now, the drift examples where indeed it was more related to aging, fouling, degradation, tempered, or miscalibrations. There's multiple reasons why data would be lying or data is not really reflecting the actual state. And for drift, it's more like linked to sensor health, where indeed it's linked to the physics, first principles, or the environmental conditions. But there's more typical reasons why data is not really representing the actual state of the system. And then we talk more about data health, data quality artifacts, where indeed it can be things that are introduced in the data pipeline, things from timing issues, synchronization problems. In IoT, you have also a lot of issues with transmission, processing integration, things like compression problems, but also problems linked to metadata, where indeed the context or the tags are not completely fully right configured, but also things like missing values, duplicates, corruption, but also inconsistent granularity. So step back, let's talk more about drift. Our approach as time series related to drift is a lot can be checked related to sensor data. So our approach is having multiple of checks done all the time, things like checking for flatlining sensors, spikes, outliers, gaps, noise, bias, unit problems. And the approach is typically that you would combine all these data checks together linked to a certain group of elements. For example, for pressure measurements, are you going to check if these measurements will be drifting in combination with noise, but also like, I know that the pressure measurement is always correlated with something else, checking if those correlations will be broken. So our approach to this is that if you want to make an abstraction on saying if data can be trusted, you need to check multiple things at the same time for similar kind of groups. Doing that at scale, that is how, as Timeshere, we are approaching data quality management. Now, back to you, Thomas. Impact of sensor drift. Two questions there. The impact of sensor drift linked to operations, but also the impact of drift linked to data products. Can you please weigh in on that?
Sure. Well, to start, in systems that are sensor rich, drift is really inevitable. So it does occur whether you want it or not. And the real question is not if it happens, but how fast you notice that it happens and how easy you can identify whether the behavior is truly problematic, whether there is impact or not. And that impact is indeed playing on, let's say, a short time ranges on the operational side, but it's also happening on a longer time frame, more on downstream processes. And so to give some examples, if you think about operations itself, it starts with safety. If you have safety instrumentation systems, for instance, that depend on redundant sensors, then you'd better monitor whether those redundant sensors are telling the same story, yes or no, because if one of them is drifting, you need to repair, you need to take action. If you don't, you're compromising safety. Another example on the operational side would be control loops. Many factories have control loops to keep things operating at the right levels and regimes. If the sensors that are used in those loops are drifting, then a perfectly tuned loop can go bad, right? It can start oscillating, it can start saturating, and you might have quality issues, for instance, with the product you're producing. You might be consuming more energy than you want. So there's all kinds of problems that this can lead to. If you move more on the right side, so on the, let's say, longer time frames, then if you think about things like predictive maintenance models, then models are trained on certain data, and if your data starts drifting after you're trained, then those models will also start giving false alarms. So also on that side, it plays a big role. But it's also use cases like billing, for instance. If you're billing your customers based on measurements from flow meters, and those flow meters are drifting, they're no longer well calibrated, you're going to send wrong bills. If you have environmental sensors you use in reporting and they start drifting, you might include the wrong values in your report, which might lead to compliance issues. So data drift detection is important in all of those areas. It's kind of a smoke alarm for your use cases that leverage that data.
And then a top example that's of course very important these days is energy, because we all know that energy is a big topic. And if temperature measurement would be drifting, and you would, for example, get readings of 120 degrees, but in reality, it's like 115 degrees. And you would be indeed, like with your control group example, be controlling and like trying to optimize. I can imagine like a lot of energy loss can be linked to drift, right?
Absolutely. Energy is a big use case. We see it coming back in multiple ways. Related to the reporting side, also related to the operational side. It's certainly a case we see a lot. Yeah.
So let's dive deeper into drift. This is a one-on-one tech talk. So what's
Let's
really
get
interesting
technical.
for us is how do you detect drifts? What's a technical kind of implication? So let's please talk about that further, Thomas.
Let's start with the basics. If you're a statistician or a mathematician or a data scientist, you've probably heard of a test called the Mann-Kendall test. It's kind of the basic test everybody is using to detect drift. Without going into too much detail, it's kind of based on the comparison of values at a certain timestamp with values that come after it. And if those values are more likely to be higher than lower, so you look at the signs of the differences of those values, then you're gathering evidence that the signal might be drifting. And you're kind of building up that evidence and then doing a statistical test to score whether it's significant, yes or no. That's something called the Mann-Kendall test. And in theory, it sounds simple. You just apply that test on your data and you know whether you have drift or not. But this is where it really gets interesting, because if you want to do this in practice, you're running into all kinds of complications, because the real world is not as simple as taking a data set and running a standard Mann-Kendall test. So maybe we can look at some of those complications, because I think that's where it gets really interesting. Otherwise, you could just ask ChatGPT, how do you detect drift? And you would get the Mann-Kendall test, but we're here to dive a bit deeper. And so let's maybe start with a first complication, which is that signals are often autocorrelated. That means that if you look at values, they're not just noise, they're typically slower variations in those signals that are natural, that are not drift, but that are just typically happening and that are perfectly fine. And you need to take that into account, especially if you have slow varying signals that are highly sampled. Your Mann-Kendall test might give false alarms if you're not compensating for autocorrelation. So on the picture, you see that autocorrelation is really taking a lagged variable, let's say a delayed version of the same signal basically, and then comparing within a certain window how well the signal is correlated with its delayed version of itself, right? And that is how you build up an autocorrelation spectrum, and you can start to include that in adjusted versions of a test like Mann-Kendall to compensate for autocorrelation. This is still quite broad in the sense that if you're thinking about detecting drift in signals, you need to wonder how the signal behaves normally and what is part of the normal behavior versus what is actually meaningful drift. And this is one aspect of it. There are other complications, and one of those complications is that if you just take a naive Mann-Kendall test and you apply it on a signal that is slowly drifting versus a signal that has a step change, then it would basically fire in both cases. It would tell you that something is off in both cases, but maybe you want to make a distinction between a step change and a slow drift. And if you want to do that, you could consider adding things like a slope estimator or additional information that you're gathering about the behavior to try and see whether the slope is consistent or whether it is highly inconsistent over the period that you're assessing for drift. Because if it's highly inconsistent, it might be a step. If it's really more or less consistent, then you might pick up a gradual drift. And
if you do step changes in your process, of course, it has also a big impact then on the drift detection.
Well, we'll come to that. So many processes, or maybe we can talk about it now. Many processes have different regimes and alternate between those regimes. Say you're producing different products, for instance, or you're switching the load of a factory, or you have different phases you go through in a more cyclical process. So if you have those different regimes, then the question of detecting drift becomes more difficult because the changes between those regimes are often much more pronounced than the actual drift you're trying to pick up in terms of absolute value. So you need to somehow compensate for the differences between those regimes. This example shows different products, but it could be any type of switching in a process you can imagine. And if you look carefully, you see that there is an actual drift happening. That's why the red line is the dashed line is shown. You see that the drift is happening compared to this red line, but it's hard to pick up by a test like Mann-Kendall. If you just naively give it this data, it will not pick it up. So you need to compensate or for this stratification, if you want to call it that way, and then you get into a non-standard testing world. So there's not too many out-of-the-box algorithms you can use to do that, for instance. So that's another complication. Maybe one more I want to highlight is that we're always talking about looking at a window of data and doing a drift check on that window. But the reality is obviously that you see data and more data is coming in all the time, and you don't really know which window of data you should assess. And maybe you look at a window of data, you find drift, but the drift is not finished. It might continue into a next window, maybe overlapping, or so you need to devise a strategy that works in a continuous monitoring mindset to pick up drift that is adaptive in the windows it's assessing and takes into account that real life situation of not knowing which window exactly to test up front. So that's another, I would say, major complication of detecting drift in practice.
Some people say that you should go to real time for assessing data quality. I think for sensor data drift or drift in general, it's impossible, right? You need a batch approach because you need samples of multiple windows, if I see this example. So I think that is an impossible challenge to detect in real time.
Well, you at least need to wait until you have seen a significant amount of data before you can actually call it drift. So you cannot judge drift on a sample by sample basis. You need to buffer data. You need to, or at least buffer intermediate sufficient statistics that you need to detect a drift. And the assumption that you can just do data quality checks on individual samples and that's sufficient, that's not correct, in particular not for drift. Of course you can detect not the numbers and just mark them, but you cannot do that for drift in general. So maybe let's look at yet another complication, because I listed quite a few, because we've been working on this topic for a while, and it's interesting to see what you need to do to make it work in practice for all kinds of use cases. I have another slide on detecting drift on segments. Um, what does that mean? Well, it's not always about a continuous signal for which you need to detect drift, right? Sometimes it's more of a cyclical process that you're looking at. Maybe you have a press, and it's pressing, and then it's going to a next cycle, and it's pressing again, it's pressing again, it's pressing again, and you're measuring the pressure that is being exercised on a part. If that pressure is drifting over time, you want to know, but it's not just a continuous pressure measurement that is ramping up. There is these cycles of these operation of that equipment, and you need to cut out basically the right parts and then look at the drift of maybe the maximal peak value within a part of that cycle and how that's drifting over time. So things get more messy, more complicated if you look at cases like that. Or you have a batch process in process manufacturing, and it's cycling through different phases. And you might want to assess whether temperature measurement you're getting is actually drifting over time across all these batches to assess whether the sensor still works. Or there might be filter installations in a water system that have different phases to go through. They have backwash, they have filtration, and so on. They can be in different states. Again, typical cycles. You want to assess drift within one of these operational states over a long time. So those are cases where you need to do more work to actually get drift detection to work. And then there is an interesting other context that I wanted to emphasize, which is the context of redundant sensors. So oftentimes, if sensors are really critical, they are basically installed redundantly, meaning there are multiple sensors that are trying to measure the same thing or more or less the same thing. And the control system or the logic that is deciding on shutting down a process, for instance, safety system, it's taking all those measurements and is then comparing them and taking a vote on those measurements and then deciding what to do next. But if you're in that situation, you can actually do extra things for drift detection as well, because you know you have multiple measurements that are supposed to do the same thing, and you can start to monitor whether they're deviating, yes or no. That sounds really simple. It sounds like you're subtracting two signals and you're looking whether they're the same or not. In practice, it's more tricky than that to have a robust signal that tells you whether those different redundant sensors are drifting, yes or no. But it's certainly something that you need to consider as a special case, because if you're just doing drift detection on a single sensor here, you're not leveraging all the information you have. You need to really also factor in the redundancy properly.
When measurements are being implemented redundant, typically that's linked to because it's important, the measurement needs to be accurate. So linked to, for example, use cases like safety loops. Indeed, when one would be, or two of the three would be drifting, or one would be drifting, that's of course important to know because it was a line of defense to get redundant. And if one is drifting, you need to know it. So I think that's very important as an extra thing to detect.
It's very important that you monitor these things, and it's either for safety or it's so critical for production. It's a shutdown. It's kind of an emergency shutdown mechanism that, you don't want it to be activated because of a sensor drifting or not being calibrated properly. So you really want to know in that case, absolutely.
Just going to that slide we just discussed about detecting drift with segments, how it's done before, how it can be done with newer technologies. I can imagine yesterday or a couple of years ago when people would be sniffing around or detecting these kind of drifting measurements, they would spend a lot of time doing visual analytics. Or can you weigh in on that? Is that something you saw people doing? Or
Yes, so we still see people doing that. It might or might not be that simple, because if you look at those cycles, for instance, we were assessing drift in a minimal flow that a pump could achieve during a kind of special phase. It was occasionally going in where you could assess the minimal flow that pump was generating, and you could detect drift over time to see something was off. But you couldn't see that if you just looked at the raw signal, because the variation in that signal was just way higher than anything we were trying to see with that drift detection. So if you want to do that, even visual analytics, you need to have a very good system to filter the data, filter out all those parts that are not relevant, then graphically look at it. And you can already see that that is not an approach that scales. If you're looking at more data and you want to do this more systematically, then just looking at it visually is not going to cut it anymore. And we see all the companies equipping more and more sensors. So it's the irony is that the more data you have, the harder it actually becomes to know that data has changed or is misbehaving. And that is something that makes visual analytics, or even in general a do-it-yourself approach to data quality hard. But I think we'll come back to that topic in a minute.
Summarizing for me, doing it yourself here, visual, one reactive, and you spend a lot of time detecting it with all the steps you need to take. So it's an approach you should be doing proactively, on the fly, adaptive, because it's something that's moving over time. So you need to be warned at the right time.
Yes, yes, and it's something that is feasible. I'm describing complications here just to actually get to the bottom of the problem, and not just talk about a standard Mann-Kendall test, because the reality is more complex. But it's feasible to do this in a robust way at a quite significant scale. There are more nuances here, right? So we're talking about drift as if it's always an offset between two signals, but you also have other types of drifts. Like, for instance, you have drifts where the dynamics change gradually over time, and that's also a form of drift that might happen, for instance, when a sensor gets fouled and it's not causing a bias in the signal, an offset, but it is reacting more slowly to changes in the environment. Then that sensor is also starting to misbehave and drifting over time. It becomes not responsive anymore, unresponsive. But that's a different type of drift also to pick up. So anyway, there were some complications. I hope it helps to set the context for what drift detection really means.
Sometimes people say that you have concept drift, data drift, sensor can be drifting. Some people then link it more to data ops, other people to ML ops. Can you give your opinion, Thomas? What's the nuance here?
Yeah, we briefly talked about machine learning models in one of the cases I mentioned in the beginning, but we mostly talked about the data side of things and detecting drift and signals in a more or less absolute sense. But if you think about it, you have the data ops domain and you have the machine learning operations domain. The data ops domain is there to make the data fit for use, and the machine and to have a structural approach to managing it. And the machine learning operations is about the models and deploying them in production and keeping them maintained and so on. And in that intersection between the two, that's where you have topics like model drift happening, which is a term you might be familiar with if you're more on the machine learning side of things, because it's often used there, obviously. Now, model drift is interesting. It is related to what we just discussed, of course. But if you talk about model drift, there's two main types of drift that people usually distinguish. It's data drift and concept drift. And let me give an example to make it clear what they mean. If you're doing a predictive maintenance model for a compressor, for instance, and you've trained the model on that on certain data from that compressor, if tomorrow you're operating that compressor in a different load, typically, so your range of operation kind of changes, then the physical reality of when that compressor breaks has not really changed. So the decision boundary of what your model should do didn't really change, but the data distribution did change. So that's what we call data drift. Your model might perform less well because it wasn't really trained on that new regime equally well, but the reality is still, let's say, intact. If you're thinking about concept drift, that would be when you're replacing the compressor with another type, for instance, and that other compressor has a different failure mechanisms or has different characteristics. And so the relation between the input and the output, and the input is then the data you're measuring, the output is whether it's failing or not, has really fundamentally changed. That's what we call concept drift. So both those things are interesting to pick up. If you relate that back to sensor drift, the relation is a bit subtle, because you could say sensor drift is data drift. There's an argument to be given for that, because of course the physical reality hasn't changed when your sensor gives different values. The physical reality didn't really change. But if you look at it from the perspective of the predictive maintenance model, the situation is a bit different, because there the inputs to your model did really change. The data that you're using there did change. And so the relation between that input and your failure modes might also have changed drastically. So you could call it concept drift in that perspective. But that's, I would be more than happy to engage in further discussion with people that are, let's say, trying to sort out those concepts. There is a relation between monitoring data and detecting model drift, because obviously the inputs to the models are important to monitor, so you know that the model that you've constructed is still applicable.
Yeah, we do this talks, of course, to explain how you should do it, to give some technical details on it. One element we see indeed, and we talked about it in previous talks, is that a lot of people are in a sort of a do-it-yourself mindset. They're building these kind of checks themselves in their own kind of tooling. Can you maybe, concluding this talk, weigh in on, okay, you would be approaching this from a do-it-yourself approach. What are the complications you would be seeing? Like, what technical challenges to expect, how to overcome them, and why is maybe more like a managed approach a better solution? So can you explain a little bit your reasoning behind?
Yeah. So it's always the same story basically, that starting out is rather simple. And so you can start with a simple Mann-Kendall test on a static piece of data that you've extracted from a database, whether it's a historian or a time series data store or Databricks. Not so hard to do. Scaling that up to a more massive footprint can be challenging, and it depends on which platform you're using to do the work, how challenging that becomes. But then all those complications that we discussed kick in as well. So it's not just about having infrastructure to do a simple rule-based check or a Python script on a data set at scale. It's all those complications, right? So if you think about how are you scoring statistical significance, how are you factoring in the background characteristics of the signals, how do you update things in a continuous monitoring mindset? How do you deal with data arriving late, for instance, as well? So how do you keep track of up to what point you're certain there is drift and up to what point you still need to check? And how do you do that incremental check? How do you incorporate the context? That's another layer of complication. If you want to get real accurate and robust results, say you have those different regimes, how do you deal with those? How do you deal with templates for your asset fleets and mapping the whole thing onto a massive fleet of assets? And then if you move even further, you can, we didn't discuss that today, but you could also consider doing some cleaning on the data itself, or you want an interactive approach for people to look at results, to deal with them, to validate data explicitly or certify data explicitly, to annotate what is happening, to give explanations and comments and so on. If you take all that into the picture with some of the other complications that I didn't explicitly mention now, but if you take all of these into the picture, it becomes a really big and expensive project to build this. And so people often go into this thinking it's 20 lines of Python code to do a Mann-Kendall test on data. But then as they progress through these stages, they start realizing it's much bigger than that. And it's something that is going to cost them a lot of money if they do it themselves.
In a previous talk, we discussed stale data, and at one point you showed the difference between a conservative approach and a more like an advanced approach. For me, what was striking is the amount of false alerts, right? Like an unmanageable amount of alerts you need to take care of. I think you need to advance in these. You need to go to model-based and even go beyond to get to a manageable state of taking care of this topic.
Yes. Yes, that's what we strongly feel. If you want to scale this up, then yeah, you need to get it to scale up, not just technically, but also from a management point of view. How do you manage the configuration? How do you manage what comes out of the system? Make sure you have good summaries of things that reach the right people at the right time. I mean, that's really what is needed to take this from a theoretical exercise to something that's applicable in practice.
And total cost of ownership is always a thing. Would you say that the do-it-yourself approach, that the TOs, the total cost of ownership is unmanageable, or is like something that's complete beyond expectations, or is that what you say?
Well, it depends on where you are. It also depends on the crew of people you have on board. I can only tell you that we've been spending many man years developing a platform and system that is dedicated to doing these things. So if you think you're gonna build a platform for IoT data quality management in a couple of man months, That's not realistic. Of course, if you're in an early stage and you're just at a very small scale experimenting with things, you can do some things yourself, but you will quickly notice that it's a steeper path to be on than you might have expected.
Maybe jumping back to this one, summarizing. So checking the drift from your signals is a good thing to do at scale. Is that also how you would support the community to do this more at scale for all sensors, all fleets, or is it something really specific tied to a use case like you explained in one of the earlier slides?
It's possible for large sets of sensors. Maybe if you think about the talk we did on stale data, that's, let's say, a lower threshold to get started with than doing drift detection at a massive scale. But drift detection is certainly possible at scale as well. And we have some out-of-the-box use cases for which we enable drift detection on fleets of sensors and get good results with them. So without doing any extra work there. So yes, it's certainly possible to do this at scale today for IoT and OT data.
Okay, so thank you for having this talk with me, and looking forward to another data talk on other checks we do. So stay tuned for next time.